Hey everyone, welcome back. This is week 19 that we're working through the Boyd's convex optimization again. So last week we finished up chapter 4 with vector optimization, but this week we're starting chapter 5, which is all about duality, and specifically section 5.1, which is about the Lagrange dual function. So chapter 5 is actually the last chapter from the Boyd book I plan on covering before starting the Elements of Statistical Learning book, or the ESL book. Anyways, section 5.1 is honestly one of the most, elegant ideas in the whole book. So I'm really excited to get into it. So the big idea is this. We're going to take a constrained optimization problem and then construct a related function derived from that original problem that always gives us a lower bound on the optimal value of the original problem. And that function is always concave, even if the original problem is non-convex. So that's pretty remarkable, and by the end of this video, you'll see exactly why that's true. All right, let's start with the problem we're trying to solve. So we have the standard form as follows here. So we have M inequality constraints and P equality constraints. So importantly, we're not assuming this problem is convex. So everything we do in this section works in the general case, anything that fits under this description here. So the variables, of course, is x, and the optimal value is p star. Now, the key idea behind the Lagrangian duality is conceptually simple. Instead of handling these constraints here separately for each I here, from 1 to m and from 1 to p, sort of as hard walls the optimizer has to respect, you can remember the hyperplane, we're going to fold sort of the constraints into the objective function. We're going to put these constraints here. So we can do this by penalizing the constraint violations directly in the objective. So here's how. We now introduce a multiplier lambda, which is greater than or equal to 0 for each inequality constraint, and the multiplier v for each equality constraint here. So then we define the Lagrangian as follows. So here's the Lagrangian here. Notice that we still we have the f is 0 here, and we still want to minimize f is 0. However, for each inequality constraint f of I, for I is 1 to m, we put some penalty on it here. And we also have equality constraints. So the vector, which is so the vectors lambda, which is an R of m, and v, which is R of p, are called the dual variables of the Lagrange multiplier vectors. So think of lambda I as the price we pay per unit of violation of the ith inequality constraint, and vi as the price of the ith equality constraint. So remember, we're still trying to minimize this function. So let's say that the ith constraint is violated. That means that this f of I of x, will be instead not less than or equal to 0, but greater than or equal to 0. If that's the case, then you will have some bad value in this sum term, which increases this function, which of course you want to minimize instead of increase. So L here is just the weighted combination of the objective and all the constraint functions. Hopefully that makes sense. So what do we do with that now? So if L is the weighted combination of the objectives and the constraint functions, then the dual function defined as g lambda v is simply the infinitum of this L function. So it looks complicated, but really we're just trying to, if you don't know real analysis, just think of infinitum as the same thing as the minimum. So the minimum of this value you can take with some x in the domain. But notice that g is a function of lambda and v only. We've minimized out x. If the Lagrangian is unbounded below an x, then g of lambda v is negative infinity. Now, here's the remarkable fact. The dual function g is always concave in lambda and v, no matter what the original problem looks like. It doesn't even have to be convex. Why? This is because g is the pointwise infinitum of a family of functions lambda v, and each of these functions is affine in lambda v. So you can see this by just looking at the Lagrangian. And the pointwise infinitum of any family of affine functions is, of course, concave. So we saw this again in chapter 3. So now we get the central theorem of this section. And I want to walk you through the proof carefully because it's short and completely transparent. Okay. All right, so here's the claim that we're going to prove. The claim is that for any lambda, which is greater than or equal to 0 with respect to the R of M space, so just a reminder, this just means that every lambda I is positive, and any V, G of lambda V is less than or equal to P prime, or remember, P star. So P star is the minimum value of X that minimizes, this objective function. So in other words, every dual feasible point gives a lower bound on the optimal value of the original problem. So I'll say that again because that's really the most, not the most remarkable result, okay, but it's really remarkable. Every dual feasible point, so this dual problem came directly from just combining the objective and constraint functions. But when we solve for, find g of lambda v, we know that every dual feasible point gives a lower bound on the optimal value of the original problem. All right, so here's the proof. So we're going to construct this proof by first supposing that x tilde be any feasible point. So that is, f of I x tilde is less than or equal to 0, and h of I x tilde is equal to 0 for all I. In other words, all these constraint functions are satisfied. Then, of course, we just simply plug this into the L function here. But notice now that because we've assumed that x tilde is feasible, we know that this term, in particular, is less than or equal to 0 for each term in this summation. So for each lambda I is greater than 0. Why is this true? Because it must be feasible. So that means for positive lambda, you take a positive number, multiply it by a negative number. Why is it negative? Because we know that's feasible, so this inequality must hold. And so this whole thing must be less than or equal to 0. Likewise, a similar argument says this term is equal to 0. So this means that the L function evaluated at x tilde is less than or equal to f of 0, x tilde, because this is less than or equal to 0. But we, simple idea is that, g is just the infinitum, or if you don't know that, the minimum of L. So g must be less than or equal to L. So you just put this in the inequality. So what this means is that for every feasible x tilde, remember x tilde was totally arbitrary in the feasible set. So g lambda v is less than or equal to the infinitum, given that x tilde is feasible, of f of 0 x tilde equals p star. So just to reiterate, this g lambda v function must be a lower bound on the optimal value of the original problem. So we don't even need to know what the original problem's optimal value is. We can instead calculate g of lambda v and get a sense of what the lower bound is before we even calculated the original problem. So hopefully you start to get an idea why we call it the dual problem. Okay, so the geometry here is worth looking at. So each curve on the left plot is a Lagrangian L of x lambda for a fixed lambda. Now, as we vary lambda, we trace out different lower bounds, right? The dual function on the right records the minimum of each Lagrangian curve as a function of lambda. And you can see it's concave. And so it always stays below p star. Now, the natural question this raises is how tight of a lower bound is this dual function, g of lambda? Can we choose a lambda and a v to get g of lambda v as close to p star as possible? So this is actually the dual problem which we get into section 5.2. So a spoiler, we can actually get it as close as we want. This diagram kind of gives it away here. All right, so before we do examples, I want to give you one more piece of intuition that I think is really clarifying. So let's rewrite the original constrained problem as now a unconstrained problem, now using indicator functions. All right, so just to clarify, my claim is that this form is entirely equivalent with the standard form of optimization problem. So if you look at it for just a minute, hopefully you can convince yourself that that's true. So we have, of course, the objective function, but we've moved the inequality constraints f of I here. In the objective, we move the h of I into the objective as well. So f of I, remember, is the inequality constraints. So we require this to be negative, or zero, but not positive. And we require the equality constraints to be zero. So here we give this a value of 0 because this contributes nothing to the objective if the constraint is true, and we give it a penalty of infinity if the constraint is violated. And of course we want to minimize this, so that's bad if we give it infinity. Likewise for this expression here, a similar idea holds. So think of the indicator functions I minus and I of 0 as sort of your displeasure at the constraint violation. If a constraint is satisfied, displeasure is 0, and if it's violated, displeasure is infinity. A hard brick wall. So now what happens when we form the Lagrangian? So first, we replace the sort of hard brick wall with a soft linear penalty. So the constraint isn't sort of a wall anymore, like infinity, it's sort of a price. So you can violate the constraint, but you have to pay lambda I per unit of violation. So instead you replace I of u, the indicator function, with lambda of I, and I of 0, the indicator function for v, as v. So now the objective function becomes like this, and we see it's a familiar Lagrangian function here. So the big idea is that this is a linear penalty, lambda I times u and vi times u. But the linear penalty, the soft linear penalty, is always an underestimator of the indicator function. Why is that true? It's because lambda I u is always less than or equal to the indicator function minus of u. Likewise, v of I of u is always less than or equal to I of 0 u. So this is exactly why g of lambda v is less than or equal to p star, which we saw earlier. The soft version of the problem is always easier than the hard version, so its optimal value is always lower. So this framing, hard constraints replaced by soft penalties, is one of those ideas that keeps coming back in optimization. So you'll see this again and again well, if we continue all the way through the book, but we also see it in machine learning. Okay, so let's work through an example here. So the first example is the least squares problem with equality constraints, ax equals b. So there's no inequalities here, just p equality constraints. So let's write out the Lagrangian. Okay, so writing out the Lagrangian, so L of xv is equal to x, transpose times x, add v transpose times quantity ax minus b. The thing about L is a convex function in x, so we can set the gradient to 0. So just doing that math and solving for x, we see that the value of x which minimizes L, or the Lagrangian, is equal to negative 1/2 A transpose V. So plugging this back into the Lagrangian function, we have the following. So all I've done is I've replaced x here with this x star and plug in this value here. So just doing a bunch of messy, algebra, we get this final result here. So if you look at it, this is a concave quadratic function of v defined for all v in R of p. And the lower bound property we established earlier tells us that this following inequality has to be true. So, what's the big idea? The big idea is that we want to see or find some lower bounds on this objective function, x transpose x. And the way we do that is we constructed the Lagrangian, we minimized it, found the infinium. In this case, L was concave. We were lucky here, and we can solve for it. And then we, using the inequality condition, we know that this is a lower bound of the optimal value of x. So notice that we didn't need to solve the original problem to get this result. So this is for any choice of v, we get a valid lower bound, for free. So the next example is one that I explored a lot in my previous linear programming class, just under a different context. So this is a combinatorial type of problem that shows up in graph machine learning type problems. Okay, so the problem that I'm talking about is the following. Okay, so the problem is we're trying to minimize x transpose this W matrix times x, where W is a symmetric matrix in the n by n space. So n rows, n columns. But we're subject to this constraint where the 2 norm of x must equal to 1. So notice this forces x to take on values -1 or 1 only. So x encodes a binary labeling of n elements into 2 groups. So you can see that the feasible set is actually a set of 2 to the n possible values that x can take on. Okay, so one interpretation of this problem is we can draw this sort of diagram here. So let me explain. So this diagram is defined by the W matrix. So so each matrix entry, Wij, in this case, this specific entry is AB. So this is the row A and column B. Likewise, Wij is the row I and column J of matrix W. Wij can be interpreted as the cost of having elements I and J in the same partition. Okay? If WAB here is in the same group, so A here and B are the same group, then it's a solid line here. But if you have AD, which goes across groups 1 and -1, then you have this dashed line here. So the edges between nodes labeled with Wij is -1 or 1. And notice that this is a symmetric matrix, right? WAB is the same as WBA. So we can see that X transpose W times X is the total cost of the partition, and we want to minimize it. So again, the feasible set has 2 to the n points. So for large n, this is computationally really difficult to sort of brute force all possible values. So we need a smarter method. So let's derive the dual function. All right, so this is the dual function here. So it looks complicated, but it's not that bad. So remember the Lagrangian function. All we do is we take the objective function, we keep it there, and then we move the constraints, in this case equality constraints, move it up to the objective, and we add some weight, vi. Now the constraints, you move the 1 to the left, and you have x squared I minus 1, and you have this expression here. Simple. But notice that this entire expression is equivalent to the one on the right, which is x transpose quantity w plus the diagonal of v times x minus the sum of all entries of v. So this is a quadratic form in X. The infinitum over X depends on whether the matrix W, plus diagonal V, is quasi-semi-definite. In other words, G of V, of course, is the infinitum of the Lagrangian function, is the sum or the negative of the sum of the entries of V, as long as W plus diagonal of V is quasi-semi-definite. Otherwise, it's negative infinity. Now, why is this true? It's true because if W plus diagonal V is not quasi-semi-definite and it's less than or equal to 0, then this term is negative, right? This term is negative. So you can choose whatever V you want, and you can make this go to negative infinity. So just for practical purposes, I'm going to assume that this is true. Then that's equivalent that Vi is greater than or equal to the negative of the eigenvalue, the minimum eigenvalue of W. Okay, finally, we want to choose the tightest uniform multiplier V, which is, this value here, which is the negative lowest eigenvalue of W times 1, which is dual feasible since W plus diagonal V is greater than or equal to 0. So taking this value V, we see that the optimal value of the original problem, P star, is greater than or equal to -1 transpose V. So this gives us a lower bound of the optimal objective function. So note here, we've taken a problem with 2 to the n feasible points. And with one eigenvalue computation, we get a valid lower bound on the minimum cost partition. So as you can see, this is a generally useful thing. It's the kind of relaxation that underlies many semi-definite programming bounds, which matters a lot in modern machine learning. All right, so let's take stock of what we built today. So starting from a standard constraint problem, we defined the Lagrangian by folding constraints into the objective with multiplier weights. We then took the infinitum over X to get the dual function, which is always concave no matter what. And we also proved that any dual feasible point gives us a lower bound on P star. And we also saw the intuition via soft constraints. Then we computed two concrete dual functions, one quadratic, one spectral. So now the next question is, what's the best lower bound that we can get? So that means maximizing G of lambda V over all dual feasible lambda V, and that's what's called the Lagrange dual problem, which, if you might guess, that's what section 5.2 is all about. So for that, I'll see you next week.